Greetings of the day, sir. Today we are going to present on the topic improving physical layer security in wireless communication using diversity techniques. Due to broadcast nature in wireless networks, the transmission between legitimate users can be easily overheard by eavesdropper. Eavesdropper secretly listen to conversation between legitimate users and the sender node. In order to achieve confidential transmission, current system typically adopt cryptographic techniques such as symmetric key. In symmetric key, the data is encrypted using an encryption algorithm and the secret key is shared to the destination, and the encrypted data is decrypted at the destination using the same secret key. But however, this is also not foolproof secure, as brute force attacks still exist. So the Wiener established principles of secure communication, emphasizing importance of secrecy capacity. Secrecy capacity is the difference between the main channel link and the wiretap link. Main channel link is the line link from source to destination, and wiretap link is from source to eavesdropper. So if secrecy capacity falls below zero, the transmission between source and destination becomes insecure and eavesdropper is successful in intercepting the data. So in order to improve transmission security, the probability of occurrence of intercept should be low. So the intercept probability must be lessened. So we are using various algorithm techniques, and we will show various diversity techniques in the presentation, such as MIMO diversity, multi-user and cooperative diversity, and we'll also show mathematical model of it, and also show the results which are concluded from the code which we have generated of the mathematical model. So now I will like to call Neet for further presentation.
So, so major security needs we have is the secrecy. Secrecy refers to the need to ensure the confidentiality of transmitted data in wireless communication systems. Secrecy aims to prevent unauthorized entities such as eavesdroppers from intercepting and understanding the information being transmitted between the source and destination. Next, we have the authentication. Authentication is the process of verifying the identity of the communication parties of a wireless network to ensure the entities involved are legitimate and authorized to communicate. Uh, in Authentication plays a crucial role in establishing trust between the source, destination, and any relay nodes involved in the communication process. Then we have the data integrity. Data integrity refers to the assurance that the transmitted data remains unchanged and unaltered during the communication process. Ensuring data integrity is essential to prevent unauthorized modification or tampering of information by malicious entities. Then we have robustness. Robustness in wireless communication security. Wireless communication security refers to the system's ability to withstand and recover from various security threats, vulnerabilities, and attacks. A robust security framework is designed to resist potential disruptions, intrusions, and uh, malpractices, which is done by the eavesdropper. So, so artificial nose is used as security measure to confuse eavesdroppers during the wireless communication. The concept is to introduce an additional noise in the transmission that interferes specifically with the eavesdropper ability to decode the transmitted data. Mathematically, this is achieved by generating noise, artificial noise, denoted as Wn, in such a way that it lies in the null space of the main channel matrix Hm. The null space of the matrix represents the set of vectors that the matrix maps to zero. Therefore, by ensuring the artificial noise vector Wn satisfies the equation HMWn, which is equals to zero. The noise is designed to have no impact on the desired communication path from the source to the destination. Now I would hand over to Dev.
Okay, so this is the flowchart of how we use diversity techniques to improve physical layer security. So we have three main parts: MIMO, multiple user diversity, and cooperative diversity. MIMO and multi are applicable to various cellular and Wi-Fi networks, as they typically consist of multiple users and are equipped with multiple antennas. Cooperative diversity mechanism only applicable to those which are adopted, which have adopted the relay architecture. Example the LTE advanced system. So let's get into MIMO. It stands for multiple input, multiple output. In this system, all the network nodes, say destination or eavesdropper, all are equipped with multiple antennas, where M, ND, and NE are the number of antennas at source, destination, and eavesdropper. Here, if the source node transmits a signal to desired destination using M antennas, eavesdropper will also receive M copies of that signal for interception purpose. To defend against this, adaptive transmit process should be included at the source to increase the main channel capacity while decreasing the wiretap channel capacity. The objective of such adaptive process is to maximize the secrecy capacity of MIMO transmission. So for that, we here present three main concrete approaches: transmit beamforming, power allocation, and transmit antenna. The transmit beamforming is a signal processing technique by combining multiple transmit antennas at the source in such a way that the desired signal transmits in a particular direction. Considering eavesdropper and destination are lie in different relative uh, space to the source, the desired signal that are received at eavesdropper will experience destructive interface and become very weak. The power allocation is to maximize the main channel capacity by allocating transmit power among m different antennas at source. In this way, secrecy capacity of MIMO transmission will be significantly increased, showing the security benefit of using power allocation. In addition, transmit antenna selection is also able to improve the physical layer security, depending on whether the global CSI of main and wiretap channels is available. An optimal transmit antenna at the source node will be selected and used to transmit source signals. More specially, if both of the CSI are available, a transmit antenna with the highest secrecy capacity will be chosen. So let us consider a scenario. Consider a transmitter A, receiver B, and eavesdropper E, which are having NA, NB, and NE antennas. So here, signal SK will be the transmitted signal uh, which provided by transmitter A. Then SK now will be multiplied with NA sized weight vector WK and form a transmission signal vector XK. Now the received signal vectors of receiver and eavesdropper will be RB and RE, which here HAB is the channel matrix of MIMO channel between A and B, having dimensions of NA cross NB, and same goes with HAE. Here, NB and NE are additive wide Gaussian noise component vectors, having length of NB and NE. Now we define the SINRs, where RHABI are the CSIs of both are instantaneous CSI of B and E available to A. The notation HABI refers to the NA length channel vector of A to the ith antenna of B, and SINRs are defined for each antenna of the receiver's antenna array. Now after this, we have a simple minimization problem that can be solved. The optimization problem aims to find beamforming weight vector W that minimizes the transmit power. Here we have two constraints such that SINR at the receiver B is greater than or equal to the required threshold gamma B, that maintains a minimum quality of service for the legitimate link. Second one limits the SINR at the eavesdropper E to be less than or equal to a maximum value gamma E. This degrades the eavesdropper ability to reliably decode the transmitted signal, providing physical layer security. Now, by solving this optimization, we obtain the optimal beamforming weight W that achieves the best trade-off between transmit power minimization and satisfying the SNR constraints for legitimate communication and eavesdropper degradation. Over to Karan.
Now we will see the multi-user diversity for improving physical layer security. So in this figure, we can see that there is a base station which serves multiple users, M users, basically U1, U2 up to UM. So in cellular networks, these M users typically communicate with base station with an orthogonal multiple access mechanism like OFDMA or TDMA. OFDMA is basically orthogonal frequency division multiple access, and TDMA is time division multiple access. In OFDMA, the OFDM subcarriers are allocated to different users. That means we need to determine which user should be assigned to access and use the given OFDM subcarrier for data transmission. So traditionally, a user with the highest throughput is selected to access the given OFDM subcarrier, aiming at maximizing the transmission capacity. However, if a user is far away from a base station and experience severe propagation loss, or we can say deep fading, then it may have no choice to be selected as the best user for channel access. So user fairness should be considered in the multi-user scheduling, where two competing interests need to be balanced. Maximizing the main channel capacity while at the same time guaranteeing each user with certain opportunities to access the channel with a good resource allocation algorithm, or transmission of energy on badly fading parts of the spectrum can be avoided. Multi-user diversity with known wiretap channel. Multi-user scheduling should be performed to minimize the wiretap channel capacity and at the same time maximizing the main channel capacity. It basically balances the user fairness while maximizing the main channel capacity and minimizing the wiretap channel capacity, requiring knowledge of both main and wiretap channels. Multi-user diversity with unknown wiretap channel. So here, conventionally, multi-user scheduling is utilized when wiretap channel information (HW) is unavailable. It basically focuses only on maximizing the channel main channel capacity. Uh, it significantly enhances physical layer security by improving the main channel capacity while maintaining the wiretap channel capacity. So now over to Bhaven.
So, cooperative diversity is a powerful technique used to enhance security and reliability by using the collaboration of multiple relays in the network. So, it involves the use of multiple relay nodes to assist in transmitting a signal from source to destination. So, let's see some relay protocols. So, first is amplify and forward. In this protocol, relay simply amplifies the signal and retransmits it from source to destination. Here, nodes do not decode the signal, therefore, it is less complex. So, second is decode and forward protocol. A relay first decodes the signal and forwards it to the destination. This process introduces more complexity but gives better performance. So, let's see some perks of cooperative diversity. The first is enhancing main channel capacity. Cooperative diversity increases main channel capacity by utilizing multiple relays to create a virtual antenna array. These relays cooperate with each other to transmit beamforming. It uses constructive interference technique that enhances signal strength. The second is protecting against eavesdropping. By using cooperative beamforming, the signal strength received by the eavesdropper can be deliberately reduced using destructive interference. This makes it difficult for eavesdropper to intercept and decipher the data. Third is relay selection. best relay selection. So by choosing a node that has highest secrecy capacity or optimal positioning, we ensure that relay assisting in the transmission provides maximum security and reliability. So now Jenny will continue.
Now let's look at security evaluation of cooperative relay transmission. So the formula of capacity is log base to 1 plus SNR. For wire tape channel, this SNR would be P of HSC whole square divided by N naught. So what is SNR? SNR is P upon N naught. N naught is additive white Gaussian noise, and wire tape channel and main channel, the SNR W is equal to probability of HSC and HSD whole square divided by N naught. HSC and HSC are fading coefficients of the channel from source to eavesdropper and source to destination respectively, and they are independently exponentially distributed, and their mean value is equal to sigma square SE and sigma square SD. So then let's look at the formula of secrecy capacity. It is the difference between main link and the wire tape link. So the formula would be log base to 1 plus HSD whole square divided by N naught minus log base to 1 plus HSC of HSC whole square divided by N naught. Then we calculate intercept probability. What is intercept probability? It is the likelihood that eavesdropper can successfully listen in despite of your efforts to secure the message. It means the lower the intercept probability, the harder for the eavesdropper will be for understand what you are saying. So we equate, then we get HSC whole square, probability of HSC whole square divided by N naught is greater than probability of HSD whole square divided by N naught. So if we try to calculate intercept probability by using this formula, we get sigma square SC whole square divided by sigma square SD whole square plus sigma square SC whole square. Here we define mains to eavesdropper ratio as sigma square SD whole square upon sigma square SC whole square. In this, source node first broadcasts its signal to M relays, and the best node is selected to forward this received signal to destination. So for power constraint, we are considered equal power allocation, and thus transmit power of source to source and relay is given as P by 2. Now given M relays, we have to, it is crucial to determine which relay would be selected as the best one to assist source signal transmission. Accordingly, the best relay selection criteria is given as below. The formula for best relay selection is argument of max of HSI whole square into HID whole square divided by HSI whole square plus HID whole square. HSI means the link from source to middle layer, means I is the relays which we are selecting. So there are different relays, and accordingly I belongs to R. And for the best relay, that node will be selected, and that node will transmit to destination. Now let's look at the plot of various graphs. Here we are looking at the plot of secrecy capacity versus MER, mains to eavesdropper ratio. We have written code for this plot, and it is demonstrated from MATLAB as. So we run this code. This is the plot for this secrecy capacity versus mains to eavesdropper ratio, and the code link is also provided in the description. Code link is also provided in the report. We have considered some parameters which are given on left side, such as gamma s, sigma square SD, sigma square SR, and M. M are the number of relays which we are selecting. From graph we can see that if we increase the number of relay selection, the secrecy capacity increases, and it is good for us. So increasing number of relay is better option. Next, we will look at the intercept probability versus MER. For same parameters, when we plot intercept probability, we can see that on increasing the number of relays, the probability is less. So if intercept probability is less, then eavesdropper's chances of successfully identifying the transmission would be less. Then we look at the graph of secrecy outage probability versus transmission power. Secrecy outage probability means the probability by which the conversation is leaked outside. So if more number of relays are there, then the chances of leakage or secrecy outage would be less. And lastly, we have bit error rate versus SNR for various MIMO configurations. So we conclude that diversity techniques like MIMO and cooperative diversity are pivotal for enhancing wireless security. Also, a case study on cooperative networks highlighted boosting secrecy capacity, and future research should prioritize developing comprehensive defense mechanism against various wireless attacks. Also, optimizing trade-off between security, reliability, and throughput is essential for advancement of next-generation wireless networks. Thank you.